Okay, so moving into kind of general topic is naming ionic compounds, right? But that's going to involve talking about ions and how we get to ions in the first place, and even what ions mean. So let me make sure I turn my timer on, because this will be one where I want to make sure I don't go too long and make the video too big to upload. I'm also going to be jumping back and forth to the periodic table here. So if you have a periodic table, if you can print one out, this is a pretty good one. I'll post this one on the Moodle site under resources. You may want to kind of make some notes on a periodic table as we go along, so that might be a good thing to have here as well. So starting off with ions, what ions means, an ion represents a charged species. So what we've talked about so far in terms of atoms, they're not charged because they have the same number of positive and negatively charged pieces. We can make an ion though by either gaining electrons or losing electrons. So the electrons from the electron cloud there in the atom, you can put more electrons into that cloud, in which case you'd have more negative charges than positive, and you'd end up with a negatively charged species. And you can do the opposite. You can pull out a couple of electrons. Now there's more protons in the nucleus of that atom than there are electrons in the cloud, and now you have a net positive charge. So the two types of ions that we can have, or positive and negative ions, have their own individual name. So cation is the term for a positively charged ion, and anion is the term for a negatively charged ion. And the terminology comes from batteries. Cathode, anode is movement of negatively charged and positively charged species to the cathode or anode variously. And there's a couple ways that I've heard of to try to remember which one is which. One is that there's a T in cation, and the T looks sort of like a positive charge, so maybe that will help you remember that cat is positive. But the one I kind of like is, when you think about cations, they're cats, and cats have paws, so cations are positive. And when you say it, you've got to make the cat claw movement. So this one's a lot better in person, but it is a good way to kind of keep track of which one is which when you hear the terms cation and anion. So as an example, let me jump over to my periodic table here, and I want to start over here on the right side of the periodic table. If we start in this column right here, column number 18, this column is referred to often as noble gases. And in some cases, they're referred to as inert gases as well, although that's not as common as calling them noble gases. But inerts may be a little more appropriate because this column, all the elements in this compound are very stable. And as a result, they tend to not react with other atoms because they don't need anything. They don't want to give away electrons. They don't want to take in more electrons. They're perfectly stable exactly as they are, so they tend not to form ions. We move away from that column, and those atoms are going to tend to form ions, but they're going to form ions in a very particular way. The number of electrons carried by the elements in the noble gas column has this added stability, and that added stability will apply to other elements if they can end up with the same number of electrons as those inert gases. So if we look at this first column here, fluorine, right, and I'm going to write a little bit on my paper here and a little bit on the periodic table, so we'll try to keep them both in view. Starting with fluorine, it's got atomic number 9, so fluorine has 9 protons, and it has 9 electrons when it is neutral. Right? Now what fluorine tends to do when it undergoes a reaction is it tends to gain an electron. So plus electron. Add one more electron to fluorine. Now we have 9 protons, 10 electrons. That means there's a net negative charge, right? And we would indicate that with a little negative sign, again superscripted after the F. Right? And sometimes I like to put a circle around there, particularly when I'm writing, just so it's a little easier to tell that that's not a stray mark. right? In the textbook, you won't see the circles because typed it's a little easier to figure out. So fluorine tends to form a negative anion with a charge of -1, right? And that's because if you just add 1 electron to fluorine, now you have the same number of electrons as neon. And 10 electrons gives you that added stability, right? Well, it turns out the way the periodic table is organized, all of the columns, all the atoms in a column have similar characteristics. So chlorine, right underneath fluorine, also tends to gain 1 electron so that it can have the same number of electrons as argon. Bromine gains 1 to be like krypton. Iodine gains 1 to be like xenon, etc. Astatine could gain 1 to be like radon, but they're both radioactive, so we don't end up dealing with them very often. But that means this whole column, the common thing that is going to happen for fluorine, chlorine, bromine, and iodine when they have the opportunity is they are going to gain an electron and become negatively 1 charge. So the common ion charge for that column is -1. Right, now if we continue to move over here, oxygen has 8 electrons. Right? Its atomic number is 8, so it's got 8 protons. If it's neutral, it's got 8 electrons. Oxygen wants, or will tend to, gain 2 electrons. Again, it wants to get to the same configuration as neon. So 2 electrons would get oxygen there, 2 electrons would get sulfur, 2 argon, 2 electrons would get selenium to krypton. So that whole column, the oxygen column, those elements will tend to take on a charge of -2. Nitrogen, phosphorus, arsenic, right? Maybe you're starting to see a trend here. Nitrogen, phosphorus, arsenic, they're 3 electrons away from that number that gives added stability. So nitrogen, phosphorus, arsenic will tend to take on a charge of -3. Now, once you get over to carbon and silicon can end up with a charge of -4, right, which would be enough electrons to get to the nearest noble gas, inert gas. That's kind of rare. Carbon, silicon tend more to make compounds with a different type of bonding than what we're describing here, where the bonding is based on ions. So I'm going to put a -4 there, but I'm going to put parentheses around it because it can happen, but it's a little rare. Now, if you'll notice on the periodic table, there's a thicker line here that kind of steps down through the periodic table, and that's an important distinction because this side of the periodic table are what are referred to as non-metals. And what we've seen here, non-metals, when they form ions, they tend to make negatively charged ions. They tend to gain electrons. All the rest of the periodic table, on the left side of that thickened line there, are what are referred to as metals. Metals will do the opposite. Metals, when they interact, particularly with non-metals, will tend to lose electrons, and that will mean they take on a positive charge. Now, there's a few along the step there that can react either way. So right around the thick line are some compounds called metalloids or semi-metals. Sometimes they act like a metal, sometimes they act like a non-metal. Right? Now, if we come over here, we can get an idea of how metals are going to react. So hydrogen actually is an oddball here. Hydrogen's actually a non-metal. Even though it's all the way over here on the left side of the periodic table, it kind of tends to react like the other nonmetals. But from lithium down, right, lithium's got 3 electrons, sodium's got 11, potassium 19, right? And those are all 1 more than the preceding noble gas. So if lithium loses 1 electron, it'll look like helium in terms of its electron count. Sodium loses 1, it'll look like neon. Potassium loses 1, it'll look like argon. So here, from lithium down, all of those metals will tend to take on a charge of +1 when they make an ionic compound. They want to lose 1 electron, right? And there's a similar trend here. Beryllium, magnesium, calcium, strontium, and down this column, they are 2 electrons away from that added stability of the inert gas number of electrons. So those metals will tend to take on a charge of +2. Now, there's 1 metal over here, aluminum, right? And aluminum, even though it looks like it's closer to the right, it has 13 electrons, so it's actually closer to neon by going this way, which would mean losing electrons. So aluminum always has a charge of +3, and aluminum acts like a metal when it forms an ion. It tends to form a +3 ion, right? Now, we're going to see how these charges play into making compounds, right? But it's important also to recognize there's a whole bunch of metals in the middle here that are a little bit more complicated, and we'll have to talk about how to understand the potential positive charges that those have as we progress down through the rest of this particular page. I'm going to stop the video there, and we'll pick up in the next video.